Hey, it's Ferdinand Dandy here, and in this video, let me discuss to you the different PCBA inside this small aluminum casing. This is my new project. I call it Michelle Taka. I will going to discuss to you which one is the Arduino A3CS, the Arduino, which one is the power amplifier, the MOSFET 5-watt Class A power amplifier, which one is the regulator or the DC-DC step-down regulator, the thermostat, the DHT11, and so on and so forth. So stick around to this video, guys, till the end, and let's dive for that. All right, this is the exploded view of the project, and I wanted to start it with the power supply. So the power supply is a standard power supply, a switch mode power supply, or the so-called SMPS, that I can simply get it from the market. It's a 19-volt DC with a 3 ampere output, and this is the wire that is connected into the project to the amplifier. And in the amplifier, at the entry point, I have this DIY made circuit on the universal PCB with an electrolytic capacitors and a zero point 0.1 microfarad ceramic, adding a two blocker diode. They are in parallel because this amplifier requires a high amount of current passing through these diodes, so I made them in parallel. And the main purpose of that is that because of the long wires from the SMPS, I need to protect the amplifier from being far away from the power supply, and I use this one to improve it, improve the power supplies at the entry point. There you go, you can see that one. That is the entry point of the power supply. And I say that the switch mode power supply 19 volts is the power supply for the MOSFET power amplifier. So the MOSFET power amplifier is known as the ACA. These boards in here, this is the ACA clone. I say it's a clone because it's not the original form factor from the designer itself, Nelson Pasa. So I just say it's an ACA clone or the comp amp clone. And this is for the left channel, and this one is for the right channel. They are basically identical. The 19-volt supply is coming from this circuit and then distributed to the left and to the right via this solid state relay. This solid state relay is not just like those mechanical relays that it will click on and click off. This one is a solid state, which means to say that it is electronic relay, and it is being activated when you input a minimum of 3 volt DC and about 32 volts maximum in order for you to trigger this electronic relay. And the one that is triggering right now is the AMPduino A3CS, this one in here, by sending a logic 1 into this electronic relay. And if that will happen, the 19 volts from this circuit will be distributed into the left amplifier and then to the right amplifier. This is the AMPduino A3CS. The red one is the AMPduino A3CS shield, and beneath it is the Arduino Uno. And that one over there, that is the SW1 or the switch with LED. And in the standby mode, this one switch is actually active, meaning to say it's watching the users if someone press it, assuming that I press the switch like that, and then the Arduino A3CS will enable this solid state relay and then distribute the power to the left amplifier, then to the right amplifier. That's how the Arduino A3CS will going to control this solid state relay. What about the demo? Let's go for that. Why not? So let me have a demo right now for the power on and off. You can see that there is already the blue LED lighted on the A3CS board. And if I'm going to press the switch in here, then this solid state relay will be enabled just like this one. And you can see it's already on in here, and you can see that the amplifier in the left and in the right, their LED is already on also. So that's a simple way to control the power supply of the MOSFET amplifier, the amp for the left and for the right. If I'm going to press it again, then you can see that this LED in here, including the solid state relay, will be turned off, as you can see it right now. You can see this one. This is the a DC to DC step down from the 19 volts in here going to the input and output about 12-volt DC. So this is the one that is step down the power supply for the AMPduino from 19 volts to 12 volts. And inside the Arduino A3CS, we have another passive regulator in here, which step down the voltage to about 6 volts. And then further down to about 5.3 volts, go down to the Arduino Uno. From 19 volts to 12 volts to 6 volts down to 5.3 to the Arduino Uno. What about this board in here? Looks familiar to you? That is actually the LM2596, a DC to DC converter step down from the 19 volts to about 12 volts, which power on the VU meter to the left and to the right. It means to say that this is actually the 19 volts in here. It is controlled from the relay so that when I turn on the amplifier, the VU meter will also turn on. And when I turn off the amplifier, the VU meter will also turn off. It is being controlled. The power supply of 19 volt is controlled on the solid state relay. And these bodies in here, these are the thermostat, which is precisely will going to monitor the temperature of the heatsink, one for the left and another pair for the right. This is the 55 degrees, and that is the 65 degrees, the lower threshold and the higher threshold. And you can see in here, there's a DHT11 in here, which also monitor the air heat temperatures. I would say like that because this thermostat in here is exactly monitoring the heat on the heat sink, while the DHT11 will going to monitor the ambient temperature inside this casing. I think that's almost pretty the whole circuits and PCBAs inside this casing, except at the back. So if I'm going to flip up at the back, you can see this one. There is an exhaust fan in here. That's another one in there. That's a 12-volt exhaust fan, and also this one. So this exhaust fan actually, it is being controlled by the same DC to DC converter. Let me just say that if I turn on, the solid state relay will turn on, and we got the supply of 9 volts, and it goes to this DC to DC converter, the LM2596, which is also the supply for the fan. The fan is in there at this side and also on the side. The next part of this video is about driving the hardware with the firmware. Basically, this is a new to our DIY hobbyist, which is only concentrated on the hardware but never on the firmware. But don't worry guys, we have the DR100W concept project wherein I'm presenting right now how to program a microcontroller. To get our focus into the firmware, the Arduino sketch programming, we have to recall back our very basic programming know-how, which we learned in the previous videos, from the very basic simple blinking the LED into a more complex programming with the switch, with the debounce, timing diagrams, and the real-world optimization. Well, everything is already in here in my YouTube channel, so just keep watching guys. For now, let me add the heat monitoring to the heatsink using the thermostat KSD01F at 65 degrees and also 55 degrees, the upper and the lower threshold, and also for the DHT11. So what I've done is to test each sensors one by one, and in here I already have the program, which I rename it now to be the name of the program is Michelle Taka, which is the implementation of AMPduino A3CS, and I clearly define in here what is the program name, what's the parent program, the program description, and also the hardware in here, which is I need that kind of introduction, so anyone who will read this program will definitely can understand what I'm doing in here. And the purpose, the purpose is to use the Arduino A3CS in the real project building, which is the Class A power amplifier Michelle Chaka, and the last updated in March 2025. The key point here is that I added the microcontroller input-output pin 11 to monitor the 65 degrees shutdown, and then I make the subroutine, which is the shutdown. Let me go to that, and this is the shutdown subroutine, which means to say that if it sends the 65 degrees on the heatsink, then it will perform several instructions in here. I'm not going into the details because that's huge to discuss. I'd rather say that if you have the chance to get this program, or you wanted to have it, let me know and I will send it to you. And how I qualify this program? Well, of course, I have to test it in real worlds. So what I've done actually is that I wanted to use a blower that is used for blowing the hair to enable this KSD01F at 65 degrees. But unfortunately, it's just not gonna happen that I can produce 65 degrees at the surface of the heatsink, and that is a failure, unfortunately. But when I look at it, that I'm working at about 4 o'clock in the morning just to finish this, and I glance to my coffee. Oh my god, that coffee is warm enough to enable that 65 degrees upper threshold for a shutdown. And I have to do an unusual kind of simulation that if I'm going to make the KSD01F 65 degrees temperature sensor, and I can enable that using the coffee, why not? So I have done it, and in fact it's actually working. This is something that I never planned, but as a DIYers, there is always a way. And that's pretty cool, right? Do you agree with me, guys? The next thing for me to do is to enable the DHT11, which is I already here in my program. And the DHT11 actually requires a more complex programming with the use of the DHT libraries, as you can see in here. And you need to define the microcontroller that will going to be interfaced with the DHT11 and other kinds of parameters that are required by the library. So I just have to follow that library requirements. And also I declare an integer, which is I call it temp inside. This one is the variable that contains the temperatures read by the DHT11. I need to make a subroutine which is will perform all the kinds of instruction that I have it in my mind, and I put them into instruction. So this DHT temperature in here is the one that it is being read by the temperature, which is loaded into the temp inside. And you can see there is a delta in here. So what is this all about, the delta? So I'm comparing actually the temperature at the room temperature being read by the temperature meters, which is I am really believe in it, and compare that to the reading of the DHT11, and there seems to be a 4 degrees delta, wherein the DHT11 is much higher by 4 degrees, so I need to subtract that one. And then I'll make some instruction in here that initially I put that into the 65 degrees, but the 65 degrees cannot be able to detect by the DHT11 because the blower cannot have enough heat to blow into the sensors. So what I have done in here is that I actually changed the upper threshold to 40 degrees, which means to say that this is only for testing. So I say that 40 degrees for test with the blower only, which means that at 40 degrees I can actually enable the DHT11, and then I can log it. I can able to understand what is the performance of this subroutine when I enable the DHT11. And there you go, I able to enable it, and you can see that the LED is exactly blinking like what I intended to do, and the instruction on the Arduino sketch. Alright guys, this is just a sneak view of how the Arduino A3CS can help you to monitor and control the temperature of your power amplifier, especially for the Class A, which is really notorious to heating. And of course, you can learn, and you can only do this by knowing how to program the Arduino Uno controller. And of course, you can do that actually in a real world by learning and improve your programming know-how by following the Arduino project. Again, only here at the DR100W concept project. There will be more discussion on the application of the Arduino A3CS, the Arduino SMI, and the Arduino my music mate, in our DIY power amplifier build in the next videos. For now, enjoy the show, enjoy listening to your favorite music on your DIY made power amplifier. Bye for now, and see you in the next Arduino videos.